Hello, my name is Jordi Romeu from Universitat Politècnica de Catalunya, and in this unit we'll talk about wave propagation. When we consider wave propagation in a real environment, we have to consider the interaction of electromagnetic waves with this environment. In the outline of this unit, we'll start talking about waves in matter, then we'll consider propagation in real environments, and then we'll consider different phenomena such as reflection scattering, diffraction, atmospheric effects. We'll talk about the empirical models and some other considerations we have to take into account when we talk about radio propagation, and we'll end up with a summary. We'll start talking about waves in matter. Now, what we'll do is we're going to consider now the wave equation, as we did previously when we talk about electromagnetic waves, but when we're in a certain medium. So the set of Maxwell equations is the same, we already know them. We know that when we're in a certain medium, that medium can be characterized with the electric permittivity, epsilon, or the magnetic permeability, mu, and they relate the field intensity vectors and the flux density vectors. Epsilon r and mu r are relative values, and epsilon naught and mu naught are the values. Here you have their values in vacuum. If we have a linear homogeneous isotropic media, epsilon and mu are scalars not depending on the field intensity. And if we assume a source-free environment, that is that the charge density, the net charge density is 0, but still we can consider that there are free charges that can move, we can express the conduction current density using this expression. J, which is the current density, is sigma times the electric field, where sigma is the conductivity of the medium, which is measured in Siemens per meter. Notice that this expression at the end is nothing else than Ohm's law, that expresses the current as a function of the field. So now we're going to derive the wave equation for Maxwell equation, as we had done previously, taking the curl in Ampere's and Faraday's law, remembering that the curl of the curl is minus the Laplacian and the gradient of divergence, and we end up with a wave equation that, if we compare with the wave equation in free space, we see that we have this additional term that appears when the conductivity is different than 0. If we assume a time harmonic field, then we can substitute the derivatives and we end up with this sort of relationship, where k is the wave number in the medium, is omega square, or k square is omega square mu 0 epsilon. Now let's see a particular case of the 1D wave equation. In that case, we can assume that we have a wave propagating along the z-axis and polarized along x. Here we have the curl, the expressions of the curl. We make the proper substitutions, and taking derivatives along z and derivatives along time, we end up with the 1D wave equation. Notice again that we have this additional term that appears due to the presence of a certain conductivity in the medium. Now, if we assume time harmonic fields, this is the 1D wave equation, and it can be seen, and we'll see it right away, that that wave equation has a solution of this type, where gamma is what we will call the propagation constant, and it's a complex number that has two terms: alpha, which is the attenuation constant, and beta, that is the phase constant. If we substitute this expression into the wave equation, we end up with this expression here that has to be equal 0, so that whole term here has to be equal to 0. And remembering that gamma is a complex number, we make the substitution, we obtain this, And if this equation has to be 0, it means that both the real part and the imaginary part has to be 0. So we have those two equations, this equation here and this equation here, and the first thing that we can see is that alpha and beta are not independent, but they are related. And if we solve the equations, we end up with the values of alpha and beta. Which are those two? The attenuation constant has this expression. Notice that if the conductivity is 0, alpha is 0, and this is expression of the phase constant, beta, and notice that in that case, if sigma is 0, then what we have is that beta equals the wave number k, which is omega square root of mu epsilon. The units, alpha, its units are nepers per meter, and beta has units of radians per meter. Now, let's see the meaning of those quantities, especially alpha. Alpha measures the attenuation, or it causes the attenuation of the wave. If we have that the electric field is propagating with this expression, and we want to look how the field attenuates, and we want to express it in dBs, what we do is 20 times log of the magnitude of the field, and if we just substitute this expression, we obtain, well, this term here, and then this term that we can see that, well, we have a few constants, we have that 20, we have alpha, we have log 10 of E, and then we have Z, the distance. So what this is telling us is that the field is attenuating, is decreasing its magnitude along the propagation Z. Now, if we consider the attenuation in 1 meter, we can see that the attenuation in meter is 20 times log 10 of V times alpha, and this is 8.68 times alpha. And this is the attenuation of the wave expressed in dBs per meter, because when we did this 20 times log, we were expressing the field in dBs. So alpha, expressed in nepers per meter, at the end is the attenuation, and if we want to express that attenuation in dBs per meter, we have to multiply that value of alpha by 8.68. We usually define the penetration depth as the inverse of alpha, and that means that when when the field propagates one penetration depth, the field attenuates by 1 over E, or 8.68 dBs. Now, we're going to consider two different cases. So far, we have not made any approximations. The expressions we were using were exact. Now, we're going to consider the case of what we call dielectric. In a dielectric, that ratio, sigma over omega epsilon, is much smaller than 1. So we can take the previous expressions and make some approximations, and we can see that alpha has this expression and beta has this expression. Actually, in a dielectric, what happens is that the attenuation constant alpha is much smaller than beta. That means that beta is almost equal to k, because if alpha is very small, then beta is approximately k. And this is the expression of an approximate expression for the attenuation in a dielectric. Now, in good dielectrics, we can define a complex relative dielectric constant. This can be done if we consider a harmonic excitation, and then we take Maxwell equations in the frequency domain. Doing the right substitutions, we can see that we can define a sort of a complex dielectric constant in which we have the conductivity appearing in the imaginary part of the dielectric constant. So we can use this concept of having a complex dielectric constant in a dielectric. And usually there is one parameter which is defined as a characteristic of dielectrics, which is the loss tangent. And the loss tangent is defined in the following way. If we imagine that the dielectric constant is a complex number, have real and imaginary part, then delta is that angle, and well, the tangent of delta is the ratio between that imaginary part and the real part of the dielectric constant. So usually in a dielectric, you will usually see that they are characterized through their through the real part of the dielectric constant and their loss tangent. In the other case that we are going to consider is a good conductor. In a good conductor, that the conductivity is high, so that ratio sigma over omega epsilon is much larger than 1. So in that case, we'll start our approximation from the Maxwell equations, and we are going to consider that well, we can approximate the wave equation by this term, by this equation. And now we consider the solution of the wave equation and we solve for the propagation constant. In that case, we can see that the propagation constant gamma has this expression, and as we said before, the real part of gamma is alpha and the imaginary part of gamma is beta. And we can see that, interestingly, they are both the same. And in that case, we define the penetration depth or the skin depth as this value 1 over square root of pi frequency mu sigma. And the wave has this sort of propagation. And notice that in a good conductor, alpha and beta are the same. Also, in a good conductor, since the electric field and the magnetic field are related, we have already the solution for the electric field, so now we can solve for the magnetic field, and we realize that the magnetic field is related to the electric field, and between them there is one difference, which is a constant. That constant allows us to define the wave impedance in a conductor, which is the ratio between the electric field and the magnetic field. And, well, this is the value of the wave impedance, which is interesting to note that that wave impedance is complex. So actually, what it means is that in a conductor, the electric field and the magnetic field are not in phase. So to finish this small unit, well, when we consider propagation in matter, we realize that the propagation constant is complex. So we have a real part for the propagation constant and an imaginary part for the propagation constant. In good dielectrics, we expect to have a loss tangent much smaller than 1, and in that case the attenuation will be small. And in good conductors, notice that the field is heavily attenuated if we try to propagate inside the conductor.